Welcome to this tutorial about the optical fiber and its characteristics. Optical fibers are the fundamental media that is carrying all the light in all types of optical communications. The transmission capacity of such a fiber is enormous. One single fiber can theoretically carry about 1 million HDTV video streams over many kilometers. It is because of their high bandwidth and low loss over distance that optical fiber communication systems are so widely used today. Optical fibers can be found in home entertainment systems, and fibers can be used as patch cords between various types of equipment in a data center. And you can find fibers buried underground in large-scale public telecommunication networks. But what is really an optical fiber, and what different characteristics can it have? An optical fiber is a very thin and long cylindrical piece of pure silica glass acting as a waveguide for light. It consists of an inner core and an outer cladding enclosed in a protective coating, which in turn is surrounded by strengthening material and an outer jacket, protecting the fiber from damage and moisture. All in all, the strand of combined coating, cladding, and core is typically about the same dimension as a strand of human hair. Connecting two optical fibers is done by fusion or mechanical splicing and requires special skills and interconnection technology due to the microscopic precision required to align the fiber cores. The light waves travel down along the core, and because of the different refractive index of the core and the cladding, the light bounces back and forth inside the core instead of escaping, just as if it was reflected by a mirror. If the bend is not too sharp, this also works fine when the fiber is bent to be deployed around corners and other obstacles. When a light ray passes from one medium to another at an angle, the light ray is deflected, refracted, if the media have different refractive indices. So when a light ray enters the fiber core from the side, it is deflected and then deflected once again when it enters the cladding, which has smaller refractive index than the core. If the angle of the incoming ray towards the normal, the single alpha, is small enough, the ray will be diffracted so much at the boundary to the cladding that it is reflected into the core again. And since the core is symmetrical, the same thing will happen when such a ray reaches the other side of the core. The light ray is guided down along the core by successive reflections from the cladding. This is why it is so important to align the transceiver and fiber correctly. When we bend the fiber, the angles in the diagram are changed, and light may start to leak out of the core at each reflection. The tighter the bend, the more light will leak out, and the less light will be left to carry the signal. The bending radius of the fiber must thus be of the order of a few centimeters or more to keep the bending loss low. You should always be careful when handling and installing optical fibers so that you avoid all unnecessary bends. Just as there are many grades of copper cables, there are many grades of optical fiber. The most fundamental divide is between multimode and single-mode fiber. Fibers with core diameters that are much larger than a single wavelength of light are multimode fibers. In multimode fibers, light can travel simultaneously along many different paths, modes, along the fiber. This results in a broadening of a light pulse as it travels through the fiber. This effect, called intermodal dispersion, limits the data range and distance at which multimode optical communication systems can operate. The intermodal dispersion can, however, be reduced by grading the refractive index of the core from a maximum value at the center to a minimum value at the core cladding boundary. The fiber is then a graded index multimode fiber, whereas conventional fibers with constant refractive index in the core are known as step index multimode fibers. Irrespectively of type, multimode fibers are not suitable for distances over about 500 meters and are seldom used in telecommunications networks. But for shorter distances, for example, interconnections between switches and in-home entertainment systems, multimode fiber is common because of a lower cost for the transceivers involved. Single-mode fibers have a much smaller core on the scale of a single wavelength. Light can then only travel along one path, one single mode, along the fiber. This virtually eliminates any distortion that could result from differences in travel time and allow for much longer, higher bandwidth optical links. Single-mode fiber is also required to take advantage of the multiplexing capabilities of DWDM described earlier. Hence, single-mode fibers are used in telecommunication systems, and their characteristics have been extensively standardized by the Telecommunications Union (ITUT). Transceivers and active optical cables are available in versions supporting either of the two fiber technologies, multimode or single mode, which means that you need to keep track of what type of dark fiber you are using for your communication system. Even in single mode fibers, some of the energy of the light wave is lost when it propagates through the fiber. The signal is attenuated as a result of absorption and scattering. As shown in the diagram to the right, the attenuation depends on the wavelength of the light and is measured in decibel per kilometer, that is, dB per kilometer. In the infrared spectrum used for optical communication, a typical fiber has a minimum attenuation of some 0.20 dB per kilometer at approximately 1500 to 1600 nanometers. There are also other parts of the spectrum with reasonably low attenuation, which are often referred to as transmission windows. There is a significant increase of the attenuation around 1383 nanometers, called the water peak, since it is caused by contamination of hydroxyl ions in the glass in the manufacturing process. Attenuation is an inherent characteristic of the fiber, and the way to cope with it is to amplify the signal at regular intervals. When a short pulse of light travels through an optical fiber, its power is not only attenuated, but also dispersed in time, so that the pulse spreads into a wider time interval. We have already talked about intermodal dispersion in multimode fibers. However, there are also other types of dispersion. Chromatic dispersion is caused by the refractive index of the glass, making shorter wavelengths travel faster than longer wavelengths. Then there is also polarization mode dispersion, where different polarization directions of the signal travel with different speed and cause spreading of the input pulse. Both the chromatic and the polarization mode dispersion are bitrate dependent. That is, the higher the data rates sent over the fiber are, the worse are their impact on the signal. Special dispersion-shifted and dispersion-flattened fibers have been developed to control the dispersion into single-mode fibers. There are also passive dispersion-compensating modules that can be installed at the end of the fiber. Another way of minimizing the chromatic dispersion is to use transceivers having laser transmitters with very precise wavelengths and thus minimal bandwidth spread. Finally, certain signal modulation techniques, such as coherent modulation, can reduce the effects of the chromatic dispersion. So, when to use single mode and when to use multimode fiber? Generally speaking, single mode fiber is the most versatile alternative and a prerequisite if you plan to install a DWDM system. The cost per meter of the fiber is about the same for standard variants of both types, but the transceivers for multimode fiber are normally less expensive than the transceivers for single mode fiber, since they can use less precise lasers. It's time to summarize where we find the different types of fiber. Patch cords and shorter data center internal connections can be either single mode or multimode fiber, but they must be single mode fiber if they are to be used for DWDM. Multimode fiber is also found in home entertainment systems. Telecommunication networks, on the other hand, use almost exclusively single mode fiber due to its low loss and suitability for DWDM techniques. This ends this tutorial. To learn more about optical communications, just continue with the next tutorial in this series.